The first example is the load X instruction, which means that we're going to load register R with the current contents of memory cell X. So the first step is that we're going to send the address X, and this address is currently stored in one of the address fields of the instruction register. That's why we have the IR with the ADDR address as a subscript. So we're going to send that address to the MAR. We're then going to fetch the contents of cell X, and we're going to place that value in the MDR. And then finally, we're going to copy the contents of the MDR, which had the value of X, and then store that in register R. The next instruction is the store X instruction, which means we're going to store the contents of register R into memory cell X. So the first step is that we need to send address X, which once again is stored in the address field of the instruction register. We're going to store that in the MAR. We're then going to take the contents of register R and store that in the MDR. And then finally, we're going to use a store operation, and we're going to store the value of the MDR into memory cell X. We'll now take a look at the add X instruction, which means we're going to add the contents of cell X to the contents of register R, and then we're going to put the result back into register R. So the first step is we need to get the memory address. So we're going to send the address of X, which is currently in the address field of the instruction register, and we're going to store that in the MAR. We then need to get the contents of cell X, so we're going to use a fetch instruction, and we're going to get and place that in the MDR. We then need to get the operands into the add, the operands of the add instruction to the ALU. So we'll send one operand by taking the contents of the MDR because that has the value that was at X. So we're going to store that, put that into the ALU. And then we need to get the contents of the register. So we're going to take the contents of R and send that to the ALU as well. We're then going to execute the add. So the way we're going to do that is we're going to activate the ALU, and then we're going to select the output of the add circuit as the desired result. Remember, when we talked about the ALU, we can choose which output we want because we're going to be executing several operations. So we want the output from the add circuit. And then finally, we're going to copy that result back into the R register. We'll next take a look at the jump X instruction, which just means that we're going to jump to the instruction located in memory location X. And this is just a single step. We're going to send the address X to the program counter. That way the instruction stored there is fetched during the next fetch phase. So we're just taking the address field that's in the instruction register and send that to our program counter. That's all. We're next going to take a look at the compare X instruction, which means we're simply going to compare the contents of the memory address X with the contents of register R. So these values are going to be less than, equal to, or greater than. So we're going to see if the contents of X is less than R, if the contents of X is equal to R, or if the contents of X is greater than R. And then depending on what result we get, we're going to set the condition codes of GT, EQ, and LT to the appropriate values. And we're going to assume that all those values are initially 0. So the first step is, once again, we're going to need to get the address. So we're going to send the address of X to the MAR. So we get that from the instruction register. We're then going to need to fetch the contents of cell X and place it in the MDR. We're then also going to send the contents of address X, which was in the MDR, and send that to the ALU. And then we also need to send the contents of register R to the ALU as well. We're then going to do a subtract instruction in order to do the comparison. So what we're going to do is we'll evaluate the contents of X minus R to get the condition code. And then, so for example, let's say if the contents of X minus R is greater than 0, well, that means the contents of X was greater than R. So if that's the case, then we're going to set GT to 1. So depending on the results, we'll just set GT, EQ, or LT to 1. So if the content of X minus R is 0, then they're equal to each other. So we're going to set EQ to 1. And if the content of X minus R is less than 0, then that means we know that the contents of X is less than R, so we would set LT to 1. The last example we'll take a look at is the jump GTX instruction. So what this simply means is if the GT condition code is 1, we're going to jump to the instruction in location X. So the way we're going to do this is we're going to load the address field of the instruction register, which is the address of location X, into the program counter. Otherwise, we'll just continue to the next instruction. So this is basically how it's done. So if the GT condition code is 1, so if it equals 1, then we'll jump to the instruction at location X, which is, once again, we will load the address field to the program counter. And then that means the next time we fetch something from there, we will get the address of the next of the place we need to jump to. And if this is not the case, well, we're not going to do anything with the program counter, so we would just continue to the next instruction. The last thing we'll mention about the machine language for now is it really isn't user-friendly. I mean, it's designed for computers and machines to understand. It's not designed for us to understand. I mean, try to see if you can understand this instruction here. I have absolutely no idea what this does. And this is actually how programming was done originally. And so we were running sequences by using just a bunch of ones and zeros. And the problem with this is it's cumbersome, it's confusing, and it's very error prone. It's very easy to put in a 1 when you meant to put a 0 or vice versa. So, I mean, there were a lot of problems with trying to write strict machine code for these instructions. Fortunately, things have gotten better, and later on we're going to use abstraction to make more user-friendly programming languages.